Texas Math Mundo audience, as promised, this week we're going to tackle some variations to bearing problems. It should be a lot of fun. We're going to take a look at a couple of actual UIL problems from previous years as examples. So these are real problems encountered by students during competition. Again, variations on bearing problems right ahead. If you enjoy this material, please hit the subscription button and the notification bell. Smash that like button and make a comment below. Variations to bearing problems right ahead. My name is Samuel Cantu, and this is Texas Math Mundo. Alright, Texas Math Mundo audience, let's get started on variations to bearing problems. Last week we did the typical bearing problem when you go from point A to point B with a certain magnitude and a certain bearing, and then from point B to point C with a certain magnitude and a certain bearing. And the question typically asks, what's the distance from point A to point C? Today we're going to look at some variations. Let me lay down the groundwork for the first variation. First variation will be if you start off at point A, for example, and let's say you go to point B. So from point A to point B, and then say you go from point A to say point C. Well, the question typically asks now not from the first point to the last point, but it asks what's the distance from point B to C, this distance. And the idea is very similar. The idea is very similar to last week. We want to take, now instead of summing the horizontal components of your vector and the vertical components of your vector, I laid that groundwork last week, so I'll try to post that in the video description below so you can see the groundwork for last week. So instead of now adding the vertical components and the horizontal components, you would subtract them. This particular vector, the first one has a horizontal component that goes like this, and the other vector has a horizontal component that goes like this. Since they're opposite signs, when you subtract, and then you get a square, so when you subtract, you end up getting the complete horizontal vector from B to C. And then, similarly with vertical components, this vertical component goes upwards, and then the next one goes all the way up. So when you subtract, since they're both going the same direction, you're actually going to get the horizontal component of the vertical component of the desired vector. So you have a right triangle. By taking the differences, you have this shape, you have this side, you have this side, and by applying the Pythagorean theorem, you can get the length of the distance from B to C. So the distance would be then the square root of r sub 1 cosine theta sub 1. This is looking at the horizontal components, minus r sub 2 cosine theta sub 2, that quantity squared. And again, this is the Pythagorean theorem. You add the vertical line, which is obtained by r sub 1 sine theta sub 1, plus r sub 2, minus, my bad, let me get the eraser here. Remember, you're taking the difference in this scenario. Minus r sub 2 sine of theta sub 2, that entire quantity squared. So that's the main difference. When you're asking the points from point B to C, so you have your original point at point A, they give you a certain magnitude and bearing to point B, they give you a certain magnitude and bearing to point C, all from point A, and you want the distance from point B to C, then you would take the difference of the vectors, and that would give you your answer. So let's go ahead and look at an example. And again, I have to thank UIL for the gracious use of their problem sets. So for this particular problem, this is problem number 47 from UILB from 2019. Okay, so the problem says The Wind Gust Electric Company erected a wind turbine 1,500 yards from the main station on a bearing of 110 degrees. They erected a second wind turbine 800 yards from the main station at a bearing of 300 degrees. How far apart were the two turbines? Now, for a bearing, I'm going to use counterclockwise on the positive x-axis just to stay consistent. It doesn't matter what orientation you use as long as you're staying consistent. So let's go ahead and draw a rough picture, and then we'll do the problem. So the Wind Gust Electric Company erected a turbine 1,500 yards from the main station. So let me call this the main station right here. Main station. You want it 1,500 yards from the main station on a bearing of 110. So 90, 180, it'll be about something to that effect, and that's 1,500 yards. That's one of the turbines that they erected 1,500 yards from the main station. They erected a second turbine, so this is, I'm going to call this point B. They erected a second turbine 800 yards from the main station at a bearing of 300 degrees. So, you got 270, 360, 300, 270, maybe like this, roughly. And this was at 800 yards. Of course, this drawing is not to scale. Okay, so, and they want the distance, how far apart are the two turbines? I could probably say T sub 1 and T sub 2. And so you want the entire distance. So this is one of these variations where you got the point of origin goes to one point at a certain magnitude of bearing. That's from that same point of origin, you go to a second point with a certain magnitude and a certain bearing, and you want the distance between the 2 points. So this is one of those where you take the difference of the horizontal and vertical components, so the distance would actually equal 2, and writing it all out, we would have, so for the first one, it's 1,500 cosine, and that theta sub 1 was 110 degrees, and then minus, and then the second one was 800 cosine, and the bearing of that one was 300 degrees. And you want that entire quantity squared because we're applying the Pythagorean theorem. And in a similar way, we want the y components, the difference of the y components. So you got 1,500 sine of 110 minus 800 sine of 300, and that quantity squared. And so we just punch it into the calculator. So let's go ahead and do that. I'll go ahead and fast forward this section so it doesn't take so long. So let me go ahead and punch it into the calculator. We get that, which we want to put in approximation mode, and we get 2,292.06, and so minimizing, we get the answer 2,292.96, and the answer is C. All right, so that's one type where the point of origin remains the same. You're going to go a certain magnitude and bearing from that point of origin to one location. From that same point of origin, you're going to go a certain bearing and magnitude in another location, and you want the distance between those two locations. This time, you take the difference of the two vectors. You've got to know the math, because when they ask you these variation problems, you'll be able to deal with it. And depending on the program you have, the program maybe you have maybe written for one sort of variation problem and not for the others. Okay, so let's go ahead and do a new table and go on to the next problem. All right, now we're going to look at a second type of bearing problem. This one's slightly different from the first one. Again, we have to know the mathematics so we can deal with the variations. This one comes from the UIL district release. I believe that's the E release when the district, I forget. But this is UIL district release for the year 2019. This is number 36. Number 36. So that we can take a look. UIL district 2019, number 36. So let's read the problem. It says, salty water anchored a buoy 200 feet from its pier on a bearing of 320. Let's draw a rough picture. Salty water, that's funny. Salty water anchored a buoy 200 feet from its pier on a bearing of 320. So you got 90, 180, 270, 320 might be this ways. 200 feet. 200 feet. On a bearing of 320, he places a second buoy 100 feet from his pier on a bearing of less than 90. So somewhere in that first quadrant. And he buries at 150 feet from his pier on less than 90. What bearing would the second buoy have to be placed in order for the buoys to be 300 feet apart? So now, again, we're concerned with the distance from the buoys with a common orientation point. So you want this distance, okay? You want this distance. So let's go ahead. What you do is you know the distance now, so we can plug in for D. You need the buoys to be 300 feet apart. And that's got to equal to, and now we're going to take the difference of the x components, the difference of the y components, square them, applying the Pythagorean theorem. So for the first one, we got 200 cosine of 320 minus, and this other one is 150 cosine. I'm going to call it x, but you call it theta, you can call it whatever you want. We need, well, probably x is not the proper thing because we need the bearing. We already know that the distance is 300. All right, so I'm going to call it x, and so we square that. And then we're going to do the same thing with the vertical components. That's 200 sine of 320 minus 150 sine of x, and that quantity needs to be squared. And at this point, I think this is now a solver problem. Unless somehow you can isolate the variable, get some sort of cute sort of trig identity, maybe I haven't really explored it. At this point, I would just put it in the calculator, and that's when I'm going to proceed to do it. This calculator will probably use some sort of numerical method that they programmed in there to solve this stuff. All right, so let's go ahead and do this. Put it in the calculator. Like I said, you may try to solve it algebraically, but who knows? You might need a special trig identity, or it may be impossible. I'm not so sure if you could isolate that variable, but I haven't explored it and don't intend to. I plan to use the calculator. So let's go ahead and plug this into the calculator. Solve for x. And here's a little trick. They ask you for a bearing less than 90. So oftentimes at the end, I'll put that such that, and I'll put that such that, and I'll put 0 is less than x is less than 90. And that'll give me the answer in the specified range. I push enter, and I get 77.2796. 77.2796, and the answer would be B. All right, this one's interesting because you didn't have to get a length this time. You had to get an actual bearing. So I just used my basic understanding of the vectors and understood the type of variation to bearing problems this was, knowing I had to take the difference of the horizontal components, square them, the difference of the vertical components, square them, to then apply the Pythagorean theorem. I was able to come up with an equation, and I was able to use the solver to solve. And so these are a couple of different variations to bearing problems. I hope you enjoyed that. Thank you very much. I hope you enjoyed that, and I hope that helps you in your competition. I plan to bring many more instructional videos for your enjoyment, I hope. If you do enjoy it, please take a moment to subscribe to the channel, hit the notification bell, smash that like button, and make a comment below. Again, I hope you enjoyed it. Plenty more to come. Thank you for your support. My name is Saul Cantu, and this is Texas Math Mundo. Farewell.